Hello everyone, my name is Maria and here we're going to be covering Worksheet 2, which covers chapters 2 and 3. Okay, problem 1 talks about acids. So I put together some definitions for you. Acid gives up a proton. The pH is 1 to 6, and strong acids fully dissociate. A base is alkaline. It accepts protons. The pH is 8 to 14. Conjugate base has less protons. You're going to be hearing a lot about conjugate base and its weak acid. And they're usually a pair. And so you just have to know that the one that has more protons is the acid. So the conjugate base will be anything, the partner that has less protons. The Ka is the acid dissociation constant. The pKa is the negative log of the acid dissociation constant. Some strong acids, here's some examples: hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, and nitric acid. Here's some examples of some strong bases: potassium hydroxide, sodium hydroxide, barium hydroxide, cesium hydroxide, strontium hydroxide, calcium hydroxide, lithium hydroxide, rubidium hydroxide. It is possible for an acid to lose more than 1 hydrogens or protons. In this case, every hydrogen will have its own pKa value. Remember, when an acid loses its, well, let's start at the beginning. We want to focus on weak acids. When weak acids lose 1 proton, they will have 1 pKa. If they have 2 protons to lose, then they will have 2 pKa's. And if they have 3 protons to lose, they will have 3 pKa's. And then down here are just some formulas that I found for you. pH plus POH is equal to 14. The POH is equal to the negative log of the hydroxide ion concentration, and it's the same thing for pH. The pH is equal to the negative log of the hydrogen ion concentration. I don't have that one written here, but that's what it is. And then we have pH is equal to 14 minus the POH. Remember that anything in brackets is in molarity, so it'll be moles per liter. And then down here we have the pH is equal to the pKa plus the log of the conjugate base divided by the acid. Okay, and then right here we just have some examples of what is acidic. So again, pH of 0 to 6. At 0 you have battery acid, then lemon juice at pH of about 2, vinegar at a pH of 3, milk is at a pH of 6, baking soda and seawater are 8 and 9, milk of magnesia has a pH of 10, ammonia has a pH of 11, lye has a pH of 13, and yeah, that's the pH scale. So, okay, let's start your problem. A, does a strong acid have a greater or lesser tendency to lose its proton than a weak acid? Okay, for that question, it's literally just a definition. So, a stronger acid will have a stronger tendency to lose its proton, and that's what makes it a strong acid. B, does the strong acid have a higher or lower Ka than the weak acid? Okay, so whichever acid can produce the highest hydrogen ion concentration will have the greater Ka value. For C, does a strong acid have a higher or lower pKa? Since the definition of the pKa is that it is the negative log of the Ka, then those two are basically inversely related. If you have a high Ka value, you have a low pKa. Okay, problem 2. Calculation of the pH of a strong acid or base. A. Write out the acid dissociation reaction for hydrobromic acid. Okay, so for these problems, you're just going to go ahead and use these formulas over here, depending on what information they give you. So for A, they just want the acid dissociation reaction for hydrobromic acid. And if you remember from lecture 1 or from discussion 1 video, hydrobromic acid is one of the strong acids, which means that they fully dissociate. Okay, that's it. So hydrogen ions and bromine anions. That's what hydrobromic acid dissociates into. Okay, B. Calculate the pH of a solution of 5.5 times 10 to the negative 4 moles per liter of hydrobromic acid. So they're giving us the concentration, and you just have to find the pH. So let's go over here and see what we have. Okay, so we have the hydrogen ion concentration here, and there's the pH. So we're going to use that formula. Okay, so they're giving us the concentration of hydrobromic acid. What you have to know, because it is a strong acid and it fully dissociates, this is something that you just have to know. So the concentration of hydrobromic acid, because it fully dissociates, is equal to the concentration of hydrogen ions, and that is equal to the concentration of bromine ions. So those three are the same. So that means that actually makes everything easier for us, because now we can just plug this number in to the equation, which is pH is equal to the negative log of the hydrogen ion concentration, which in this case is 5.5 times 10 to the negative 4. Oops, 4. Okay, so the pH is equal to 3.26. Okay, so now C. Write out the acid dissociation reaction for potassium hydroxide. So now we're talking about a base. Potassium hydroxide is a strong base, and what's cool about it is that it also fully dissociates. And since this is a strong base and it fully dissociates, that means that the concentration of potassium hydroxide is equal to the concentration of potassium ions, and that is equal to the concentration of hydroxide ions, which means that we can just plug that straight into the formula. But for the formula, we're going to be using this guy now. POH is equal to the negative log of OH. But it's basically the exact same thing. So POH is equal to the negative log of the concentration of oh, okay, I guess I'm already working on D. Okay, so POH is equal to the negative log of 7.3 times 10 to the negative 5, which is equal to 4.14. So the POH is equal to 4.14. But problem D is asking for the pH. So this is a two-step process. We got the POH, and now we need the pH. Well, we have this equation up here. pH plus the POH is equal to 14. So we're just going to do that. So pH plus the POH, which we got as 4.14, is equal to 14. Then you just subtract 4.14 from both sides, and your pH is equal to. And that's it. Problem 3, identifying the conjugate base. Which is the conjugate base in each of the pairs below? So remember, here in A we have RCOOH and RCOO. The acid will have more hydrogens because it donates hydrogens, and the conjugate base will have less hydrogens. So here in A we have RCOO. This one has no hydrogens, and this one has one hydrogen, so we know that this is the conjugate base. For B, we have HNO3, which is one hydrogen, and NO3 minus. We know that this is the conjugate base. And then we have H2PO4, and we have HPO4. So this one has less hydrogens, so we know that this is the conjugate base. And then we have HCO3 and CO3 minus. This one has less hydrogens. We know that that's the conjugate base. And then, so in the worksheet, your samples look like this, your examples. But on the quiz, you had an example that looked like this. And I had a lot of questions emailed to me, so I wanted to explain. Here we have Na2, one hydrogen, and PO4. And then we have Na1Na, two hydrogens, and PO4. So first, the top one with one hydrogen, that's the conjugate base because it has less protons. And then the conjugate, or the weak acid, is the one that has two protons. So this is just going to be acid. Okay. So PO4 has a negative charge of 3. It has a -3 charge. So you need 3 elements that add up to a plus 3 to cancel it out so that the equation, or whatever it is balanced. So here we have sodium and we have hydrogens, and they have a +1. So we need to make sure that it's always 3. So here we have 2 sodiums, so that's +2. And we have 1 hydrogen, so that's +1. So that's a +3, which balances out the -3 over here in the phosphate. And then for down here, we have sodium 1, and then we have 2 hydrogens. So that's +3. That balances out the -3. So that's why the sodium changed on the quiz. Okay, you decide to prepare a phosphate buffer from solid sodium dihydrogen phosphate. So here we have 2 hydrogens and disodium hydrogen phosphate. So here we have 1 hydrogen. Okay, so that tells us that this is the base. It has less hydrogens, and this is the acid. It has more hydrogens. Okay, and you need 1 liter. You need a pH of 6, total phosphate concentration of 0.150 moles per liter. Okay, hint, phosphoric acid is a triprotic acid. If you remember correctly, that just means that this acid has 3 hydrogens that it could donate, and it donates each hydrogen at a different pH. So that's what the pKa values represent: 2.14, 6.86, and 12.4. A, identify the acid and its conjugate base in this buffer system. We already did that. B, which pKa value is relevant for the preparation of this buffer? Well, we've got 2.14, we have 6.86, and 12.4. All we have to do is find the buffering range. So 2.14 minus 1 is 1.14, and 2.14 plus 1 is 3.14. That's the range of that one. 6.86 minus 1 is 5.86, and 6.86 plus 1 is 7.86. Okay, and 12.14 minus 1 is 11.14. 12.14 plus 1 is 13.4. Oh, I think I said something weird, but anyhow, this is what it is. So now, they want the pH to be 6 for this buffer. They told us up here. So the first buffer doesn't work because 6 would have to fall in between here somewhere. The second one, this one works because 6 falls within that. And the third one doesn't work because 6 does not fall within that. So this would be our buffer. The pKa value would be 6.86. Problem 4, Part C. Determine the weight in grams of sodium dihydrogen phosphate. Let's get my pen. Sodium dihydrogen phosphate, so this is the acid. Write that down, acid. Okay, and disodium hydrogen phosphate. This one had 1 hydrogen, so that's the base. Okay, needed to prepare this buffer. Okay, so they're giving you, they want the weight in grams. So we're dealing with concentrations of both the conjugate base and the acid. If you look over here, the only one of these formulas that has both is this one. See, that's the concentration of the conjugate base and the acid. So this is the one that we're going to be using. It's always possible that you'll need 2 or 3 of these formulas depending on the problem, but for now this is what we need. Okay, we also know that a total phosphate concentration of 0.150 moles. So that's a given. So we know that the HPO4 concentrate, the HPO4 plus the H2PO4. Okay, so this is the conjugate base plus the concentration of the conjugate acid is equal to 0.150 moles per liter, because it's molarity. And they also told us that we need 1 liter, so that's just 1 liter. You multiply it and you cancel out the liter. So the concentration of our base plus the concentration of our acid is a total of 0.150 moles. Okay, so now we can go ahead and start plugging things into the formula. So we're going to have pH is equal to the pKa plus the log of the conjugate base over the acid. Okay, so we just plug in all of the information that we have. So we have everything except for this, because that is our unknown. That's what we're trying to solve for. So the pH was 6. They told us up here, right here, that the pH is 6 is equal to, and the pKa that we determined in the previous problem that was relevant was 6.86 plus the log of this, the conjugate base over the conjugate acid. Okay, so the first thing we do is subtract 6.86 from both sides, minus 6.86. Okay, crosses that out, and then 6 minus 6.86 is equal to 0, it's negative 0.86. And that equals the log of the conjugate base over the conjugate acid. So here you can actually write HPO4 and H2PO4 if you want to, but it's just easier to write it this way. Okay, so now we want to get rid of the log, so you just do 10 to the power of all this and 10 to the power of that, because you have to do it on both sides. Okay, 10 to the power of negative 0.86 is equal to 0.138, and that is equal to the concentration of the conjugate base Yeah, because the 10 and the log were canceled over the conjugate acid. Okay, so now what we're going to do is kind of like a substitution reaction. So we're just going to go ahead and bring up this acid. So we're going to continue over here. It's going to equal to 0.138 of this acid is equal to the conjugate base. So now I'll go ahead and write it correctly. So 0.138 of our acid, which is H2PO4, is equal to our conjugate base, which is HPO4. Okay. So now we can do our substitution reaction. So all we're going to do is we're going to plug this value in for the next time we see the base. Okay. Okay, so we use our formula again, H2PO4 plus HPO4 is equal to 0.150 moles. So here's where the substitution comes in. So we're going to use these numbers instead of this HPO4. So we're not going to use the HPO4 right here. Instead, we're going to substitute it with this, because we know that 0.138 times the acid is equal to the concentration of HPO4 minus. Okay, so we're just going to rewrite that. So H2PO4 concentration plus 0.138 times the concentration of H2PO4. Okay, so now if you take a look at this, the number inside of the brackets is the same, H2PO4 and H2PO4. So all you do is you add these. Remember, in front of the brackets, there's always a 1. So 1 plus 0.138. Okay, so that's going to equal 1.138. And then in brackets, we have the H2PO4. Okay? Okay, so we have this value, and then we can move forward. Okay, so now we can set this value. Actually, let me erase this right here. Yeah. Okay, so we can actually set this value equal to 0.150 moles. And then you just divide by 1.138, cancels out, and then you just divide the other side by 1.138. And you get your total acid concentration is equal to 0.131. So that's the acid concentration. To get the base concentration, it's super easy. You just do 0.150 moles and you subtract. Sorry, you don't divide, you subtract. You subtract and this amount of 0.131. Okay, and then you get, okay, so you get 0.019 moles of the base. Okay, now that we know how many moles of each we have, so for the base, let's see, base, it was 0.019 for the acid, it was, how much was the acid? I think it was, let's see, acid was 0.131 moles. Okay, so this is the easy part. They gave us the grams per mole for each of these. So for our base, there was this right here, and it was 142 grams per mole. So we just do times. We want to make sure, oops, let me erase that. Okay, so times. And we want to make sure to keep the moles on the bottom so that they can cancel out. And we want our answer to be in grams because that's what they're asking for. So we just do 142 grams per mole. The moles cancel out. We multiply. That's 2.7 grams of the base. Okay, for the acid, you do the same thing. Times, we keep our moles on the bottom. We want the answer to be in grams. And we were given, our acid is over here, 138 grams per mole. So 138, moles cancel out. Our answer will be in grams equals 18.1 grams. So as long as your answer is similar to this, like almost exact or exact, then you know that you're doing it correctly. Problem 5. Phosphate buffer. A. What is the pH of a mixture of 0.045 moles per liter of sodium dihydrogen phosphate and 0.055 molars of disodium hydrogen phosphate? Okay, so here they're giving us the concentrations in molarity, which is moles per liter, of the acid and its conjugate base. So we're going to go ahead and find our formula. The only one that talks about both concentrations is this one. So we're going to go ahead and use that. So pH is equal to the pKa plus the log of the conjugate base over the acid. Okay, so this is our, well actually that's what they gave us. So they also gave us the pKa and we want to find out the pH. Okay, so this is our unknown. So pH is equal to, now the pKa that we found was useful for phosphate is 6.86. So plus the log of the concentration of the conjugate base, which, let's see, this one has 2 hydrogens, so that's an acid. And this one has 1 hydrogen. Oh no, this one has 2 hydrogens, so this is the acid. Let's go ahead and erase that. Okay, this one had 2 sodiums, but only 1 hydrogen, so this is the base. Okay, so for the base, it always goes on top. We had 0.055. Okay, and then for the acid, we had 0.045. Okay. All right, so we just have to do the math, and that'll give us the pH. So the pH is equal to okay, so they gave us the concentrations for an acid and its conjugate base. We just plug them into the formula, and our answer is that the pH is equal to 6.95. 5b. If 1 ml of 10 molar sodium hydroxide is added to a liter of buffer prepared in A, how much will the pH change? Okay, so we know that the pH was, let me write here. Okay, we know that the pH was 6.95, and they want to know how much pH changes if you add a strong base. Well, how much base are you adding? Let's see. You do 1 ml, because they said 1 ml, and you have to convert that to liters because molarity is in liters, moles per liter. So 1 mil would be 10 to the negative 3 liters times 10 moles per liter. Liters cancel out, and this equals 0.01 moles of sodium hydroxide. So you're adding 0.01 moles of this strong base, which will fully dissociate. And so if you're adding a base, you're expecting the pH to go up. We don't know how much yet, but it's going to go up. Okay, so we also know that we started off with 0.045 moles of, what was this, the acid, and we had 0.055 moles of the base in this situation. So what you're supposed to do is, I'll start off with the acid. So for the acid, we had 0.045 moles minus 0.01 moles, because you had an acid and you're adding base. So that's why you subtract from the acid. So you end up with 0.035 moles of the acid. And for the base, you end up with 0.055 moles plus 0.01. So we had base and we're adding more base, so that's why we add it. And you end up with 0.065 moles of the base. Now you just plug in these new concentrations into the equation where you're allowed to do concentrations of the acid and the base. That's the only one. So we do, so they want to know what the new pH is. So we just do pH is equal to, the pKa was 6.86. We're still using the one from the previous problem because we're still talking about the same acid base buffer system. Okay, plus the log of, and then this is where we insert our new concentrations. So the new concentration of the base is 0.065 over the new concentration of the acid, which is 0.035. And that equals 7.13. Okay, so we started off with a pH of 6.95. We added 0.01 moles of base. We expected the pH to go up, and it did. It went up to 7.13. So it barely went up, but it did go up. So let's see by how much it went up. So you just go 7.13 minus 6.95. Okay, and it went up by 0.18. That's not much, and that's because this is an acid base buffer system, and that's the power of it. You can add a little bit of base, or you can add a little bit of acid, and the pH is not supposed to fluctuate that much. C. If 1 ml of 10 molar sodium hydroxide is added to a liter of pure water at pH 7, what is the final pH? Okay, so now we're not adding a strong base to a buffer system. We're only adding it to water. So 1 ml again is, where's my pen? Actually, I'm going to write in white. Okay, so 1 ml is actually 10 to the negative 3 liters times 10 moles per liter, because they said it's 10 molarity right here. Okay, liters cancel out, and this is equal to 0.01 moles of sodium hydroxide. Okay, so now I had some students who were confused after this point. They assumed that we would be using this formula to find the pH, but we can't use this formula because we don't have, see in the formula you have a conjugate base and an acid. We don't have both of those. We only have a conjugate base, the sodium hydroxide. So we have to use this formula. The pOH is equal to the negative log of the hydroxide ion concentration. So we just do that. pOH is equal to the negative log of the hydroxide ion concentration. So in this case, it's supposed to be 0.01. So the pOH is equal to 2. Okay, so this was step 1, because in problem C, they're asking you, what is the final pH? We have the pOH, which is 2, so now we have to use another formula. pH plus pOH is equal to 14. Okay, so we have pH plus the pOH is 2 is equal to 14. So now we just subtract 2 from both sides, and we get 12. Okay, so basically this just tells you that when we added a strong base to our acid buffer system, the pH only went up a tiny little bit, but when we added the same exact amount of strong base to water, the pH went up drastically from 7 to 12. So this is why buffering systems are so important in our bodies, because they maintain everything. Otherwise, enzymes can't work properly and all that. It's just a disaster. Our pH range has to be within a very small range. A lot of students were having questions about this table, and this is super important. So this column, you have amino acids. So they have them grouped by their groups. Nonpolar, aliphatic R groups, aromatic R groups, polar uncharged, positively charged, and negatively charged. And then, let me draw something for you. Okay, so every amino acid has the NH3+. Okay, every amino acid has the NH3+. And every amino acid has a COOH. Every amino acid has a hydrogen. The only thing that changes is the R group. So we're going to talk about glycine. So what's special about the amino group and the carboxyl group is that they both have a proton to donate. So they are ionizable. And back to the table, we have the pK1. So that is in reference to the pH at which the carboxyl group will donate its proton. So for glycine, the pKa is 2.34. And for the pK2 is the amino group, and it's 9.6. So again, those are in reference to the pH at which those groups will donate their protons, because they won't donate their proton just at any pH. It's pretty specific. And then some amino groups, so remember we have 20 amino acids, okay? Now, some of those amino acids in their R group, they do not have any protons to donate. But some of those amino acids do. They have a protein to donate. So those guys have an extra pKa value, and it's this one. It's called a pKr because it comes from the R group. So here you see that tyrosine's pKa value is 10.07. Cysteine has a pKa or pKr value of 8.18. all of our positively charged amino acids also have pKr values, and all of our negatively charged amino acids have pKr values. Okay, so a lot of students had questions in lecture 4 about the titration curve. So I wanted to explain to you the glycine one first, and then I'll explain to you a more complicated one. So let's see here. So based on the table that I showed you previously, glycine does not have an ionizable R group. So let me go ahead and draw it for you. So here we have our alpha carbon in the middle, we have our hydrogen, our COOH, and our NH3. So remember, that is what all of the amino acids share. And then the R group is what is different. So for glycine, it just has a hydrogen. And so it doesn't have an ionizable R group. But the carboxylic acid is ionizable with a pKa value of 2.34. And the amino group is ionizable with a pKa value of 9.60. So here on the left-hand side, the y-axis is our pH. So we have a pH of 0, pH of 7, and pH of 13. And on the x-axis, we have the hydroxide. Because this is a titration curve, you're adding hydroxide equivalents until you get to the very end. And when you get to the very end, that means that everything that should be ionized has been ionized. Okay, so then we have, let's go ahead and start up here. So this is the same thing as this, but they just wrote it in a linear fashion. Here's your amino group, your carboxyl group, and your CH2. So you have C down here, H, and then CH. So it's just CH2. So they just wrote it a little differently. So remember that the carboxyl group has a pKa value of 2.34. And that just means, what is the pKa value? Well, let's remember. That just means that when the pH is equal to the pKa value, it means that half of these glycines, because let's say that there's 100 in solution, half of them have donated their proton and the other half have not. That's all that means. So it's basically when the pKa will tell you when that group is ready to donate its protons. So for the carboxylic acid, it's at a pH of 2.34, and for the amino group, it's at a pH of 9.6. So now, all of these 1, 2, 3, 4, 5, these areas right here, you have to be able to find them on this titration curve graph. And it seems really complicated at first, but it's really easy. Okay, so we'll start here. So notice that the amino group has its 3 hydrogens and it's positively charged. So that means that the amino group has not been ionized. And then the carboxyl group still has its hydrogen. It doesn't have a negative charge. So where is this molecule, where is it located on the graph? Well, it's located over here at a pH of 0. So at a pH of 0, none of the groups have been ionized. Now, at a pK 1, so the first pKa, we know that it belongs to the carboxyl group, the COOH. And so at a pK 1 is equal to 2.31. So this is where the pH is equal to 2.31. So we just go across, and then this area, that's where the pH is equal to the pKa of the carboxylic acid. And that value is 2.34. So what do we see at that value for the molecule? Well, we have our NH3+, we have our COOH. Half of the molecules, if there was 100, so 50 of them, are doing this. The COOH has not donated its proton. And the other half are doing this. It's a COO minus. So this half has donated its proton. And that's all that this pKa value means. And then over here, I don't think we went over it. It's just fully protonated. That's where the NH3 at the pH of 0, NH3 plus, and COOH. That is what we saw here at a pH of 0. Okay, so the pKa value 1 is right here. So we've identified those two on the graph. So let's move on to the next one. Let's see here. We have our fully protonated NH3 plus, and we have our COO minus. So finally, all of the carboxyl groups, not just 50 of them, all of them, have donated their proton. So that happens at this location in the graph, right here. So at this point, that's what you're seeing. So I'm going to go ahead and circle it. That's right here. So you have your NH3 plus, and all of your COOHs have donated the H. So now you just have a COO minus. Okay? So now let's go to our second pKa. So that's pK2. And this one belongs to the amino group. So we know that the pKa for the amino group is 9.60. So at a pH of 9.60, we just follow that all the way through, and where they cross, that's the pKa2. So this is where the pH is equal to the pK2. So the pH is 9.60 and the pK2 is 9.60. What do we see here? Well, we see that half of the molecules still have their hydrogen for the NH3. They still have their hydrogen. They haven't donated yet. And then we see the COO minus. So from now on, as we go higher up on the pH scale, we're not going to see any more COOHs. All of the COOHs have donated their protons. So we're only going to see COO minus. And then over here, we're going to see that half of the amino groups have donated their protons. So that's why it's NH2 instead of NH3 plus. So at the pK2, half of the amino groups have donated their proton and half of them have not. Okay, so now, so that area, we're just going to go ahead and draw, is right there. Okay, so now we have to find this on the graph. We have our NH2, so all of the amino groups have donated their proton, and all of the carboxyl groups have donated their proton. So this area happens right here. It's at the end of the titration curve, and that is all you see. NH2, because all of the NH3 have donated their proton, and COO minus, because of all the carboxyl groups have donated their proton. So the higher the pKa value, the greater the pH needed to remove the proton. So for the carboxyl group, because the pKa value is so low at 2.34, that's when it would start losing the proton. And for the amino group, because the pKa value is so high at 9.6, that's why it loses its proton up here. Okay, so another question that a lot of students had were about charge. And this sounds really complicated, but it's super easy. So in this group here, we see that we have an NH3 plus. So we have this positive charge here. And there's no other charges. There's none. So the overall net charge for this molecule at this stage is just a +1. And that's it, +1. Okay, how about for this one? We have a positive charge and we have a negative charge. So they actually cancel out, and we have a net charge of 0. So whichever molecule it is that we have a net charge of 0, that is our PI, isoelectric point. Wherever we have a net charge of 0, that is our isoelectric point. Okay, and then the third one. So here The N, the amino group, doesn't have any charge, but the carboxyl group has a negative charge. So the overall net charge for this molecule is -1. And it's it. That's how easy it is to determine the net charge. Okay, so then I wanted to address a question that a student asked in class. Why is this not a good buffer at a pH of 7? So remember, the best buffering regions are plus and -1 of the pKa value. In this case, the carboxyl group has a pKa value of 2.34. So the best buffering region would be 2.34 minus 1, which is 1.34, and 2.34 plus 1, which is 3.34. So yeah, the best buffering for this carboxyl group down here would be from 1.34 to 3.34. And so that's not good for a pH of 7 because pH of 7 would have to be somewhere inside of this, and it's not. So how about the pKa for the amino group of 9.6? Well, if you take away 9.6 minus 1, it's 8.6. And then if you do 9.6 plus 1, it would be 10.6. So 7 does not fall inside of these either. That's why this whole buffering system would not be good for a pH of 7. It's that easy. Okay, so this is another slide from lecture 4, but this one has an ionizable R group. So here we're looking at glutamate. So it's hard to tell, but if you remember from this table, these are the ionizable R groups, and glutamate is down here, and the pKa value is 4.25. So remember, every amino acid is going to have this amino region that is ionizable, so it can donate a proton. And then they will also have this carboxyl region, ionizable, and can donate a proton. Oh, whoops, that one's up here, sorry. So these are the backbone, COOH and NH3+. All of the amino acids have that. And then this right here is the R group. And so glutamate just happens to have another COOH in its R group. So that's why it has a pKa value. And we know that the pKa value is 4.25 because of this table. And then this table will also tell you what the ionizable value is for the COOH and also for the amino group. So it's too small to see it down here, but we have it right here, 2.91 for its carboxyl group, and then it's 9.67 for its amino group. Let's go ahead and write that down. Let's see. 9.67. This one is 2.19. And then for the R group, we know that it's 4.25. So we just write that down, 4.25. Okay, so remember, on the y-axis, we have our pH. And I kind of covered it with the table, but pH of 0 here, pH of 4.25 here, pH of 2.19 here, pH of 8, pH of 10. Okay, pH. And then on the x-axis, we have how much hydroxyl we're adding, how much hydroxide we're adding. So 1 equivalent to 3 equivalents. And then up here at the very top is when everything has been ionized. Down here at the very bottom, at the 0, is when nothing has been ionized. So let's see here. We have to find all of these let me get my pointer. Okay, we have to find all of these. So like 1, 2, 3, 4, 5, 6, 7 items. We have to find all these 7 items on this graph. You have to know where they are and what they look like. Okay, so the first one, where do we find this? Everything has its proton. The amino group has not lost its proton. the carboxyl group has not lost its proton, and in the R group, it has not, the carboxyl group there has not lost its proton. So I drew a green arrow, you'll find that at the 0, okay? Nothing has lost its proton there. Okay, yeah. And then we go to the pK1. So this should be where the first pKa value, so the lowest, in this case it's this 2.19. So this is the backbone carboxylic acid. That's where it loses its protons. So we go down here, this is the pH of 2.19. You go across, and this is where you have your pK1 is equal to the pH. So 2.19 is the pH, and that equals the pKa value for this carboxylic acid, which is 2.19. So what is happening here? Well, half of these guys have donated their proton, and half of them have not. So that's all that's happening. And then we go to our third guy here. So notice that here, let me circle that. Okay. So now we're here. And notice that here, all of the backbone carboxylic acids have donated their proton. So now we have a negative charge. The amino groups have not donated their proton. And the side chain amino, or the side chain carboxylic acid, has not donated its proton. So where is this on the table? It's just right here. That's the value. Okay, and the pH is 3.22. Okay, so now pKr. So now the pKa for the R value, and we know that it's right here, it's 4.25. So the pH here is 4.25, and you follow it across, and at this dot you know that the pKa value for the side chain is equal to the pH, which is 4.25. And here what you're seeing is that half of this carboxylic acid side chains, half of them have donated their proton, and half of them have not. Okay, so then we have this figure here, and what do you notice? The carboxylic acid in the backbone had already donated its proton at about 2.19, and now the side chain carboxylic acid has also donated its proton. All of them have donated their proton. And yeah, so that, and then the amino groups, none of them have donated their proton. So that happens at this point here. Okay. And then we go to the pK2. So now we're talking about the amino acid right here, the amino acid. At the pK2 is 9.67. So that just means that the pH is 9.67, and it matches the Ka for the amino group in the backbone. So that's 9.67. So pH is equal to pKa. And what does that mean? It means that half of the molecules have donated the hydrogen that belongs to the amine, and half of them have not. Okay? And then we go to this last section here. And we notice that the backbone carboxyl, all of them have that negative charge still. They all donated their proton. And then for the R group carboxyl, all of them donated their proton. And then the amine, notice that we no longer have an NH3+. Now we just have an NH2. So all of the amino groups have donated their protons. Well, that happens right here at the end of the titration curve. Okay, so now we have to determine where is the isoelectric point. And I know a lot of students had questions about that. Let's go ahead and do the charges in purple. So here at this first section, we have the amino has a charge, a plus, and this carboxyl does not have a charge, and this carboxyl does not have a charge. So we just have a charge of plus 1. Okay, that's our charge, plus 1. Okay, now over here, let me get my pointer. Over here, we have a negative charge from the carboxyl group, a positive charge from this group, and no charge from this group. So this positive and this negative cancel out, and so that gives us a charge of 0. Let me get my purple, so 0. So what does it mean when you have a net charge of 0? That means that this is your isoelectric point, and that happened at a pH of 3.22. That is our isoelectric point. Okay, so then we'll just keep going. Over here, we have a negative charge here, we have a positive charge here, and a negative charge here. So this positive and this negative cancel out, and then we're just left with this minus 1. So we'll go ahead and write that down. The net charge here is minus 1. Okay, and then over here we have a negative charge, we have no charge for the amine, and we have a negative charge here. So we're left with a negative 2, a net charge of negative 2. And that's it. This was a more complicated one, but that's it.